All right, everyone. We are going to be looking at the example number 5 from the notes. The notes on chapters 3, 5, and we're going to be looking at example 5 from the equations. Okay, here we go. Example 5. This problem is a little bit tougher than number 6, so there's a couple parts to this. So let's go ahead and take a look here and what we got. Oops. So, example 5 says a person is moving up in a hot air balloon at a constant speed of 2 meters every second when a ball is dropped. Okay, so he's moving up. Him and the ball are both moving up. He drops the ball as they're both moving up. Calculate the ball's velocity and position. Now this is key, relative to the balloon after 3 seconds. Okay. So here's some things here. We are going to find the velocity and position relative to the balloon. Okay, that's the key to this problem, is that's relative to the balloon after 3 seconds. Okay, so let's draw a picture here. So we'll start off by drawing a picture. Okay, so here's the balloon here. Always draw a picture. Here's the balloon initially. Okay, there it is. And we'll call this, okay, initial position of the balloon, and that will be our origin. Okay, remember we get to choose where our origin's at. That's going to be the origin here for our balloon. Okay, and at this moment, that's when the ball gets dropped. Okay, that's the moment the ball gets dropped, is right here. Okay, so what's going to happen is the ball is going to be moving up, and it's going to fall back down to some position down here. We'll call this the position of the ball. This is the position of the ball after it has fallen after 3 seconds. Okay, so that's the position of the ball. We don't know what that is. Okay. Okay, so we have this distance right here in which the ball falls. And we also have, while the ball is falling, the balloon is still moving up, right? The balloon still moves up to some position here while the ball is falling. Remember, 3 seconds, the ball falls for 3 seconds. During that 3 seconds, the balloon also is moving up. So let's draw this moving up. Okay, so this ends up being, we'll call the position of the balloon. And that's going to be equal to, we don't know what that's equal to, question mark right here. So that's a big question mark. This is a big question mark. Let's figure out what we do know in terms of our given. So here's a picture again. The balloon's moving up. Okay, the balloon's moving up. Okay, at our 0 position, we drop the ball. The ball falls after 3 seconds. The question is, what's the position of the ball? So what we're going to do, here's the game plan, what we're going to do. We're going to find how far the balloon moves up in 3 seconds. Okay, that's what this distance represents. We're going to find how far the ball falls in 3 seconds. We're going to add these two up. Okay, right? Because we want to find, if we add these up, that'll give us the total distance that the balloon is from the ball. Okay, we'll call that D total or something. Doesn't matter, D total. Okay? That's a game plan. We're going to find this. We'll find this. We'll add them up, and we'll get the total distance of the ball. We'll get the position of the ball relative to the balloon. So what do we know? We know the time. Time is 3 seconds. The person is moving up in the hot air balloon at a constant speed of 2 meters per second. So the initial velocity of the balloon and the initial velocity of the ball are both 2 meters every second. Okay? 2 meters every second relative to what? Well, we're going to say that the speed is relative to someone who's not moving, or we can say is relative to the ground, or relative to like the still air, you could say. Both the balloon and the ball, because the ball is moving with the balloon initially, right? When it's moving up, it's a positive 2 meters every second. Okay? What's the acceleration? Well, the acceleration of what? Well, when we drop the ball is going to accelerate. Okay, it's going to accelerate at what's called a constant of little g. Okay, so the acceleration that we're going to be using is actually little g, which is the acceleration due to gravity, which is negative 9.80 meters per second squared. This is a constant right here, g. This right here is a constant we'll be using throughout the entire year. So the acceleration of the ball is actually going to be negative 9.8. And we'll say the initial position of both the ball and the balloon is going to be 0. Because we're saying this, where the ball is dropped, is our origin. Okay. Sorry about snapping. I was making sure that the microphone was working. So first, let's find. So we'll do this in two parts. First, let's find the position of the ball. So we'll call this the ball position. Okay. Look at the 4 equations we can use. We need to find a position. Okay. So it needs to have d in it. It needs to have an a in it because the ball is going to be accelerating. Okay. And the only equation in which I see a d and an a, and actually a time too, as a time in there because of the ball falls for 3 seconds, would be equation number 2 that I see. Okay. So we have the position is equal to the initial position plus VIT plus FAT squared. Because our initial position is 0, we can get rid of this initial position here. Okay. And let's see if we have all the other variables. This will tell us the distance at which the ball travels. We know the initial velocity is plus 2. We know the time is 3. And we know the acceleration of the ball is going to be equal to the acceleration of gravity, which is negative 9.8. And we know the time is going to be 3 seconds. We have everything. So let's go ahead and solve this, shall we? Okay. So we have d of the, this will actually be d of the ball. So let's just call it that right now. So we don't get this confused. The distance or position of the ball is going to be equal to vi, which is 2, times time, which is 3, plus 1/2. Now be careful here. The ball is accelerating downward, so it would be negative 9.8 times the time, 3 seconds squared. Okay. So what we're going to be doing is we'll calculate this. We're squaring this. This will be 9 actually. 9 times negative 9.8 divided by 2 plus looks like 6. You end up with a final position of the ball of negative 38.1 meters. Okay. So the ball is going to be 38.1 meters below this origin right here. Okay, so this would be negative 38.1. Just write that in there. Oops. No, it'd be this actually. So from here to here, 38.1. Okay. Let's go ahead now and find the. Let's go ahead and find the position of the balloon. The balloon moves up at a constant rate. Okay, it's moving up at a constant rate of 2 meters every second. This is actually pretty easy to find. Moves up at a constant rate of 2 meters every second for a certain amount of time. The question is, how far did it move? Okay, so let's go ahead and find this for the balloon. We can use the simple equation: the velocity of the balloon is equal to its displacement over time. We're going to find the displacement here, so we'll have to solve this for displacement. V times t equals the displacement. I just multiplied by t on each side. Okay, velocity is 2. The time is 3. This equals the displacement. So the displacement is equal to 6.00 meters. So that was pretty simple. So the balloon moved up 6 meters. So from here to here, 6 meters. Okay, that's the balloon. That's this. The position of the balloon. So the question now remains: well, what's the difference between the two positions? So let's find the change in position of these two positions here. So we have a negative 38.1 minus 6. Okay, so I'm supposed to find the difference between these two, 0.00. That gave me a difference of negative 40, so I'm adding the opposite. We get negative 44.1 meters. Okay, that equals the position of the, well, there's going to be a lot of subscripts here, but the position of the ball relative to the balloon. Okay. What this says is that the ball is 44.1 meters below the balloon. You can also write that too, just 44.1 meters below. You need to have that below on there, otherwise you gotta have a direction on there. Okay, so this negative signifies there's a direction, meaning below, or you can just write it as 44.1 meters below the balloon. That would also work. Okay, see how that works? A little tough, because the tough part about this is that the balloon is moving after the ball is up. Also, the ball does have an initial velocity right away. So we're not done yet. Let's find the ball's velocity relative to the balloon. We already know the balloon's velocity is 2 meters every second. Let's find the ball's velocity now. Okay, so let me just kind of divide this up here. We get some room. Okay, so let's find the v of the ball. Okay, just the velocity of the ball. We already know the velocity of the balloon, and then we can add those up. Okay, find the difference of them. So here we go. Final velocity. So let's use equation number 1. The final velocity of the ball is going to be equal to its initial velocity plus acceleration times time. Okay. Final velocity of the ball. This is relative to the ground, or relative to being still. Okay, the ball does have an initial velocity of 2. Again, what's its acceleration? Its acceleration is going to be the acceleration due to gravity, which is negative 9.8. And how long does it fall for? Well, it falls for 3 seconds. Okay. If you multiply and add those together, you get a negative 27.4 meters every second. Okay, or you can say this is 27.4 meters every second down. Would be another way of saying that, right? Because of that negative. So the ball is moving 2 meters every second up. The ball is moving 27.4 meters every second down. So let's find the well, I don't know my pictures in there. Let's find the change in these two, okay, or the difference of the two. So we got negative 27.4 minus the balloon's moving up at 2 meters every second. Okay, and that will equal a total of negative 29.4 meters every second. So guys, this is the we'll call this velocity of the ball relative to the balloon. And that will equal negative 29.4 meters every second. So if you were standing in the balloon and you had a radar gun pointed at the ball, the radar gun would read the ball as moving as negative 29.4 meters every second. Because you are moving 2 meters every second upward, the ball is moving 27.4 meters downward. So relative to the ball relative to the balloon would be the difference of the two. So it would be a total of 29.4 meters every second. So guys, this problem's tough, I understand. But just in a problem like this, draw a picture and break it up into sections. Okay, so again, we did the ball position, the balloon position, added them up, and then we already know the velocity of the balloon, we found the velocity of the ball, added those up as well. Or you'd say finding the difference, the position velocity difference would be the same thing. Okay, sounds good. See you later.